Hello everybody, this is Maths Guy channel again, and today we are going to be going through predominantly solving a system of equations. But before I get to that, I think it's best to elaborate on some of the points I made in the previous video. So let's say we use f of x equals x. The vertical lines test is when, so for example, we have an equation x equals 1 for example, and here we have a step. And this is the vertical line, the visual representation of that line. So if this line crosses the function once, then it passes the vertical line test. There's also another test on top of this, the horizontal line test. Do the same thing, and the function, and if a function also satisfies both the vertical line test and the horizontal line test, it is a one-to-one function. Not all functions satisfy this. So for example, one of those examples, x squared. Okay, so here, whatever. The function here still satisfies the vertical line test, in which each x coordinate will always have one corresponding y coordinate. But as you can see here, as I move this equation up and down, that you see that at origin it touches 0, 0, but above that, when the range is above 0, that the line crosses has one y value has two unique x values paired up with it. So this, by definition, is not a one-to-one correspondence. Also, in high school notation, f of x is more commonly used, but in the younger year levels, you probably see y equals x squared, but in essence, it is the same thing. Okay, so now to solving a system of linear equations. This refers to when you have two or more, but mainly two equations that you want to solve for. So let's say, for example, we have f of x equals to mx plus c. Okay, you can leave it as that. When we say f of x equals x plus 1. So as you can see here, there are three types of cases with the solving of linear equations. This is actually a bad example. So let's just leave x plus 1 here. Let's say f of x equals minus 2 x plus 3. Okay. So here, we have two scenarios. So here, we have the first case where these two equations do not have the same gradient. This is a 1 in front. Let's say they don't have the same gradient, and the y-intercept is different, meaning that these two functions only intersect at this point. So that we can solve for. The second scenario is when, for example, the gradient is the same. The gradients of the two functions are the same, but the y-intercepts are different. So both of these functions are parallel because the gradients are the same, but the y-intercepts are different. So that they do not touch or intersect anywhere else. The last case is when both the gradient and the y-intercepts are the same. This means that these two functions are exactly the same and will have infinitely many solutions. I've used one just as an example to clarify, but you can substitute any constant such as k and to solve this. So one of the equations, example of the equation would be so you have kx plus 3y, or f of x for consistency. So 3 times f of x equals 1. Then you have 4x plus 3 times k times f of x equals 0. Okay, so we can call this the first function and the second function. And let's say, for example, we want to ask for a unique solution. So, which means, like in the first example, where these two functions have different gradients, and the unique solution means that the two functions intersect at one point, like this. Okay. And to solve it, first we need to pair the gradients. So solve the gradients to see what happens. So let's just grab the first function here, for instance, and you end up with f of x equal 1 over 3 minus bracket k times x divided by 3. So the gradient of this function is negative k on 3. Okay. Just make a clear distinction there. Okay, now for the second function, f of x equals minus 4x divided by 3k. So the gradient of this function is minus 4 on 3k. So after this, you equate these two gradients, so m1, m2. So minus k on 3 equals 4 over 3k. I should make it clearer. This is a bracket here. Okay. And when you're solving this, when the k is since there's a k at the bottom in this function here, it's simply best to multiply the whole both sides by k. So you have 3k squared equals 12, and k equals plus minus 2. Okay. So what this tells us is that when k is equal to plus or minus 2, these functions are the same. So the correct answer is k. The constant k is for these two functions to have a unique solution. K is every number except minus 2 or 2. And if I just provide an example of that, so say let's set okay, so k of x plus 3 f of x equals 1. Just leave it there. We have 4k. Actually, it's easier for me rather to do this. To go. So for the first function, f of x, after changing the subject, f of x equals 1 over 3 minus k over 3 x. Yep. Okay. And the second one, f of x equals to minus 4 over 3k x. Okay. Why is it not? So if I'm moving this, both functions are moving. If I set here both functions as 2, we have two parallel lines where each line does not, as you see, does not touch each other at k equals 2. Or in the same way, negative 2, both lines do not touch, because the gradients are the same. So because of that, any number in between, you see here, will always have a point of intersection. And that is how you solve a system of linear equations. That'll be all.